Natural numbers are the counting numbers we use to enumerate discrete objects. They represent quantities you can count on your fingers: 1 apple, 2 chairs, 3 books. These are the numbers that answer the question, how many, when the answer is a positive whole amount. Mathematically, we denote this set as n, which equals the set containing 1, 2, 3, 4, and so on. It's important to note that 0 is not a natural number. Natural numbers start from 1. However, some definitions do include 0. There are 2 conventions in mathematics regarding whether 0 is a natural number. The traditional convention excludes 0. This is used primarily in number theory. The alternative convention includes 0. This is written as n subscript 0, or sometimes as the whole numbers. This convention is used in set theory and logic. In this series, we use the traditional definition. 0 is not part of n. 0 belongs to the whole numbers, which we'll cover in the next video. Always check which convention is being used when reading mathematical texts. Natural numbers are built using the successor function. The successor function s maps n to n plus 1. Watch how this generates the entire set. Starting with 1, we apply s to get 2. Apply s to 2, we get 3. Apply s to 3, we get 4. Apply s to 4, we get 5. This pattern continues indefinitely. The successor function has an important property. Every natural number has exactly one successor. Formally, s is a function from n to n. This simple function gives us 3 fundamental properties of natural numbers. First, 1 has no predecessor in n. It's the starting point. Second, all of n is generated from 1 by repeatedly applying s. Every natural number can be reached by starting at 1 and applying the successor function some number of times. Third, there is no maximum element. For any natural number you choose, applying s gives you a larger one. The set is infinite. Now let's examine which operations we can perform with natural numbers. In algebra, we say a set is closed under an operation if performing that operation on elements of the set always gives you another element in the same set. This property determines which operations we can use freely within a number system. Addition is closed on n. For all a and b in n, a plus b is also in n. For example, 3 plus 5 equals 8. This works. No matter which natural numbers you add, the result is always a natural number. Multiplication is also closed on n. For all a and b in n, a times b is also in n. For example, 4 times 7 equals 28. This works. Multiplying any 2 natural numbers always produces another natural number. But subtraction is not closed on n. Look at 3 minus 5. What is the result? There exist natural numbers a and b where a minus b is not in n. Subtraction is not always defined on natural numbers. Division is also not closed on n. Look at 7 divided by 3. What is the result? There exist natural numbers a and b where a divided by b is not in n. Division is not always defined on natural numbers. These limitations tell us that n alone is insufficient for general arithmetic. This motivates expanding to the integers, denoted z, which will solve the subtraction problem, and eventually to the rational numbers, denoted q, which will solve the division problem. We'll discuss integers and rational numbers in a later lesson. We've seen which operations work on n. Now let's examine a structural property that makes natural numbers unique. The well-ordering property states that every non-empty subset of n has a minimum element. Let me show you what this means with examples. Example 1. Consider a finite subset. S equals the set containing 5, 12, 3, 89, and 7. When we arrange these in order, we get 3, 5, 7, 12, 89. The minimum of S is 3. Example 2. Consider an infinite subset. E equals the set containing 2, 4, 6, 8, 10, and so on. This is the set of even natural numbers. Even though this set is infinite, the minimum of E is 2. Why does this property matter? It's the foundation for mathematical induction. It also distinguishes n from other number systems. Consider the integers. Z equals the set of all integers from -infinity to +infinity. Z has no minimum element. This is what makes natural numbers special. Natural numbers serve two distinct purposes, cardinality and ordinality. Cardinal use case answers the question how many. The absolute value of set A equals 5. This measures quantity or size. Ordinal use case answers the question which position. We describe positions as first, second, third, fourth, fifth. This describes order in a sequence. Same numbers, different contexts. When you see a natural number, the context tells you whether it's measuring quantity or describing position. Let's examine why n is insufficient for general arithmetic. What works is 5 minus 3 equals 2. When a is greater than b, subtraction is defined. What fails is 3 minus 5 equals what? When a is less than b, there is no solution in n. Another failure is 4 minus 4 equals what? When a equals b, there is no solution in n. For subtraction to always work, we need this property. A minus b equals c must have a solution for all a and b in n. To achieve this, we need additive inverses. We need an additive identity. These requirements force us to expand the number system. Next, we'll introduce the whole numbers, the set of natural numbers with 0 included. The set contains 0, 1, 2, 3, 4, and so on. 0 is the additive identity. Adding 0 to any number returns that same number. Thank you for watching. Subscribe, like, and share to help us create more videos.